Welcome to the Explainer. All right, let's talk about a word you hear everywhere in tech these days, containers. But what in the world is one, for real? So here's how we're going to break it down. First, we'll bust some of the most common myths. Then I'm going to show you the surprisingly simple truth behind it all. We'll dig into why we even need them in the first place, see how the operating system pulls off this incredible magic trick, and then, finally, we'll see where all those big name tools like Docker and Kubernetes actually fit into the puzzle. All right, first things first, let's tackle the answers you've probably heard a million times. Heck, you might have even given them yourself when someone asks about containers. If you walk up to someone in tech and ask, hey, what's a container? You're going to get a few classic answers. And look, they sound pretty good. They even touch on all the benefits, but they almost always miss the fundamental point, what a container actually is. Yeah, these are what I like to call the diplomatic answers. And I mean, they're not really wrong, are they? They talk about all the great stuff, like making apps portable or bundling up dependencies. But it's kind of like describing an iceberg by only talking about the tiny bit you can see above the water. They tell you what containers do, but not what they are. They describe the effect, not the cause. Okay, so to really get it, we have to strip away all the jargon. Let's forget about the IT world for just a second and start with the most basic building block of any modern computer. Think about it. Every single thing your computer is doing right now, from playing this presentation to tracking your mouse cursor, it's all just a process. It's a program that's running, and the operating system gives each and every one a unique ID, kind of like a license plate to keep track of it all. And boom, there it is. That's the big secret. A container isn't some tiny little computer or a magic box. It is just a plain old process, a regular program that's been given a special kind of isolation, walled off from everything else. It's so important to get this. We are not creating a lightweight virtual machine. We are just taking a normal process that's already running and telling the operating system, hey, draw a virtual fence around this one. And that's what we call a container. Okay, hold on. That brings up a pretty big question, right? If all these processes are still running on the same operating system, on the same machine, why in the world would we bother putting them in these little boxes? This slide just nails the problem we used to have. On the left, picture total chaos. You've got a Python app, a Java app, a C++ app, and they're all in a free-for-all, fighting over the same memory, the same CPU, the same system libraries. But now look at the right side. With containers, it's completely different. Each app gets its own little bubble, its own guaranteed slice of the pie, even though they're all neighbors living on the exact same machine. And that old way of doing things, oh man, it was a nightmare. You'd have one greedy app just devour all the memory, and boom, everything else on the server crashes. Or even worse, you'd get stuck in dependency hell. This app needs version 1 of a library, that one needs version 2, and they just can't live together. The only fix was crazy expensive. Buy a whole new server or spin up a super slow, heavy virtual machine. All that just to keep your apps from fighting with each other. So, what's the magic trick here? How can one single operating system create all these separate little worlds on one computer? Well, the answer lies in two super clever features that have actually been part of the Linux kernel for a long, long time. All right, these two technologies are the secret sauce. First up, namespaces. This is what creates the illusion of a private box. It basically tricks a process into thinking it's all alone on the computer, with its own private network, its own file system, you name it. Then you have control groups, or Cgroups. Think of them as the bouncers at a club. They're the resource police. They're the ones that say, okay, Python process, you get exactly 200 megs of RAM and 10% of the CPU, not a byte more. Namespaces build the walls, Cgroups enforce the rules. This analogy just makes it all click. Imagine you're at a huge community feast. The old way is everyone just mobbing the buffet table, a total free-for-all, it's chaos. But the container way? It's like the organizers gave everyone their own personal meal box. The food all came from the same kitchen, right? The resources are the same, but now everyone gets their own perfectly portioned, isolated meal. That is exactly what namespaces and Cgroups do for your computer's resources. Now here's the thing. You could technically do all of this stuff by hand, using these low-level kernel commands. But trust me, it is an absolute pain. It's super complex, super tedious, and that is where all the tools you've actually heard of finally enter the picture. I mean, seriously? To launch just one of these isolated processes manually, you'd be sitting there typing out dozens of low-level commands. It just doesn't scale. It's not something you can do in the real world. So we needed a simpler,
automated way to just tell the OS kernel, hey, please run this process in a box, and here are the rules. This table lays it all out beautifully. Let's start at the very bottom, at the middle. You've got runc. This is the grunt. It's the bare bones tool that actually does the work of talking to the kernel and creating that isolated process. One level up, you have containerd. It's like the foreman on a construction site. It manages the whole lifecycle of the container, and it uses runc to do the heavy lifting. Then we get to the tool everyone knows, Docker. Docker is the user-friendly architect. It gives us the simple command line and the Docker files so we as humans can easily tell containerd what to build. And way up at the top, that's Kubernetes. It's the city planner. It's not just managing one container, it's orchestrating thousands of them across a whole fleet of machines. So what about that image file we're always talking about, like a Docker image? Well, it's not a tiny little operating system. The best way to think about it is like a recipe. It's just a file with a list of instructions. Start with this, copy these files, and then run this command. So when you tell Docker to run an image, you're just telling it to follow that recipe to create a new isolated process.
So if you remember one thing from all this, let it be this. A container isn't a thing. It's a condition. It's just a normal process that the operating system kernel has wrapped in virtual walls and given a strict allowance. Everything is still running on one OS, just with some really smart, really efficient partitioning.
And that brings us to a final, kind of a funny thought. If a container is just an isolated process, and Kubernetes is a tool for managing millions of those processes across a global fleet of servers, did we just spend the last decade building the world's most sophisticated and powerful task manager? Something to think about. Thanks for joining this explainer.